everyone, I'm Sophia. I'm a sophomore at Stanford University, and today I'm going to be showing you a proof of the central limit theorem. So something that is central to the proof is the idea that there exists a continuous bijection between the space of cumulative distribution functions and the space of characteristic functions. I'm going to break this down to a few pieces, so don't worry about what characteristic functions are at the moment. So first, I'm going to start with defining what is a bijection. I have an example from here, from this set of real numbers to another set of real numbers. I'm just going to call them x and y so you know which set I'm talking about. And here we have a function f that maps from x to y. So every number in x has exactly 1 point in y. So for example, 1 maps to 4 and only 4, 2 maps to 5, 3 maps to 6, and 4 maps to 7. Likewise, any point that you have here in y, it came from exactly 1 point in x. So if I'm given like a 6, you know that that must have come from a 3. So coming over here, we have the mapping where f goes from the space of cumulative distribution functions to the space of characteristic functions. The bijection is defined explicitly by this. You don't need to really worry about that yet, but just know that this is a function that has already been defined. So here, every single cumulative distribution function, it has exactly one characteristic function over here, and every characteristic function over here has exactly one cumulative distribution function. These are actually the characteristic functions, just to kind of give you a sense of what they look like. With these square root of negative ones, going forward in the video, I will just be using I. Nowhere in this video will I be an index for anything, so when you see I, that will be square root of negative 1. So the next part I'm going to talk about is how the function is continuous in both directions. I'm going to again give our analogy from the set of real numbers to the set of real numbers. So what does this mean? If you take a sequence on one of the sets, so in this case, let's say the sequence goes 5, then 4.5, 4.25, 4.125, and it's getting closer and closer and closer to some point, in this case 4. The continuous property gives us, if you take the corresponding sequence in x, so 5 goes with 2, 4.5 goes with 1.5, 4.25 goes with 1.25, this sequence defined to be the inverse function of these points. Because this function is continuous, that means that whatever this sequence converges to, in this case 4, that means that if we take the inverse function of that, and since if we put 4 on this side, then that means it has to be 1 plus 3. So then this number has to be a 1. So this sequence is going to converge to 1. And that makes sense if you think about what this looks like instead of our numbers. And so then if you go over here, we're going to now do the same exact thing, only this time it's going to be the space of cumulative distribution functions and the characteristic functions. So let's say you have some cumulative distribution function for an arbitrary random variable. If we map this over here, we can get a corresponding characteristic function. So let's say we have a sequence of characteristic functions over here, and these converge to some point, which looks like this function right here. That means that if you take the corresponding cumulative distribution functions over here, the sequence of cumulative distribution functions on this side is going to get closer and closer to whatever this thing maps from. In this case, it's a squiggle that looks something like this. And so then because this bijects onto this and so forth, that means that this sequence of cumulative distribution functions is going to converge to this. So let's connect what we've been doing to the central limit theorem itself. So what is the statement? You've probably seen this in class before, that x1 through xn be independent identically distributed random variables. Then this expression of xn's, which I'm going to call this whole expression y sub n, as the number of samples increases, this converges to a random variable that is distributed normally with a mean 0 and variance 1. Looking at a picture version of what this means, we have this diagram here. Given some arbitrary cumulative distribution function with the random variable, as the number of samples increases, our sample mean gets closer and closer to distributed like a normal cumulative distribution function. So now, what does this have to do with this expression? It's a little bit funny looking, but it's something that would make it a little bit easier. I'm going to define some intermediary variables. So first, Zn is literally just scaling xn to have mean 0 and variance 1. The square root of n times the mean of the zj's. And so then this expression, if you just plug in this for if you plug in this for each zj, then you do end up with this expression. Moving on over here, and we'll go into this in more detail later as it comes up in the proof. But for now, let's just go over what the format of this proof is going to be like. We're going to be using the continuous bijection between the two spaces. We're going to have 3 steps. The first, given a random distribution for a random variable, we're going to, so let's say it's this one. for when we have n samples of it, we're going to map this over and determine what its characteristic function is. This will be step 1. Step 2, we're going to show, as n goes to infinity, we're going to show that the limit of this characteristic function is going to converge to this. This meaning the characteristic function e to the negative t squared over 2. And then our final step is going to be showing that this is the characteristic function for a normal distribution. The reason why this is important, if you remember what we were just doing with the continuity, if we have a sequence here, and we have that's getting closer and closer and closer to this function, the bijection over here, which starting with y1, this function goes with this one, we have our left-right arrows, and we have our arrows going back and forth. As the sequence approaches this point, and then reaches this point, that means that the sequence of cumulative distribution functions over here, that sequence is also going to converge to normal distribution. And that is exactly the same as the centennial theorem, and so we are done. So now let's define what a characteristic function is. So the characteristic function phi equals this, where x is a random variable. Let's go over an example so we can get something that looks a little bit more function-like than the expectation of e to the square root of negative 1 tx. Let's say x is, for example, distributed as a Bernoulli variable with probability of 0.2. So because x is Bernoulli, there's two possibilities. X could be 0 or x could be 1. If x is 0, that's going to happen with probability of 0.8. If x is 0, this whole exponent becomes 0, so we have e to the 0, which is just 1. So 0.8 times 1. Next, we have a 0.2 chance that x is going to be 1. If x is 1, this product here becomes it. So we just have 2 e to the it. As then this would be our characteristic function that corresponds to the random variable x that's distributed as a Bernoulli variable. So now that we've broken the proof apart into 3 pieces, we're going to go ahead and start to prove the first piece. So the first thing we're trying to do is, given n samples, we want to find what the characteristic function of y sub n is. The formula is going to be that the characteristic function is 1 plus t squared over 2n plus some more terms on the order of t cubed over n to the 3 halves, that whole thing to the power of n. At this point, you have no particular reason to have any intuition why this is true, but after we do 2 lemmas to get there first, hopefully this will make a bit more sense why it's the case. So for the first lemma, we calculate the characteristic function for a single zj. The main insights for this proof are using a Taylor expansion and linearity of expectation. The rest of it is pretty much just algebra, which I'm showing here. The next lemma we solve for the characteristic function of y sub n, which is what we want eventually, in terms of the characteristic function of z sub n, which we found in lemma 1. This is where it becomes important that the x sub j's are IID, so then the z sub j's are also IID. Then we just combine the lemmas and we're done. So now we move on to step 2. Here we're trying to show that when we take the limit of n, and don't forget from part 1, this is the formula that we come up with, that this is going to converge to the following characteristic function that looks like this, e to the negative t squared over 2. Okay, so great. So let's now take this thing, and we're going to take the limit of it. Now, the thing with this term is it's going to go away very quickly. In fact, a lot faster than this term. So therefore, we can just drop it. So now, this looks like something that might be very familiar to you from calculus class. You might recall the following formula. So this is exactly what we're going to be using here. And in particular, this is our x. And so we're done. I would just like to say that I am well into the double digits for the number of times I've attempted this clip. I thought I had a good one yesterday evening, but then when I got back to my dorm at 1 in the morning, I discovered that in fact it was blurry. So now I'm here again the next day to try it again. So now that we've completed steps 1 and 2 of the proof, now we're going to go on to step 3. But first, a quick recap. In step 1, we showed that this is the characteristic function for when we have n samples of a random variable. Next, we showed that when we take the limit as n goes to infinity, meaning we're taking more and more samples, that this characteristic function converges to this characteristic function right here. In step 3, what we're going to show is that this characteristic function is the characteristic function for a normal distribution. And because of that, and if you recall from the beginning, we're talking about the continuity and the bijection. Because we have a continuous bijection between this space and this space, then that means, since we've shown that this converges to this, that means that this converges to that. In other words, as the number of samples we take goes to infinity, the cumulative distribution function converges to that of a normal distribution, and that is exactly what we wanted to show. So once we have done step 3, we have completed the proof. Since it is difficult to integrate imaginary numbers, we start with this lemma. We next integrate things. Numbers happen, and what we end up with, we recognize as the PDF of a unit Gaussian. Then we just plug in IT for s and we are done. Those of you with a background in analysis might have noticed I glossed over many steps that went too beyond the scope of CS 109. Glossed steps include the statement of proof of Levy continuity, distinguishing between continuity and sequential continuity, pointwise convergence of functions, properties of analytic functions, moment-generating functions, why we can drop the big O term. Consult your math professor or my attached write-up to see if the full proof of CLT is right for you. So that's it for my proof. I hope you enjoyed and learned a lot. Thank you so much for watching, and I'll see you in my next video. Bye!